We want to understand how to compute the surface area of a solid of revolution. So here's a xy plane, and assumes that we have a curve, say this curve, y equal to f of x, where x from A to B. And we will revolve the region, for example, the region under this curve, about the x-axis. So we will revolve this region about the x-axis. So for example, this is a curve y equal to f of x. When we revolve this about x-axis, we get this solid. Now we want to compute the surface area of this surface. As we usually done before, we will decompose this surface into smaller pieces. We will compute the surface area of the small pieces like this. For example, this one, compute the surface area of each one of them, and then we take a sum. Then we get the surface area of the whole solid. So that is the idea. So we decompose this solid into smaller pieces. So we get a partition of the segment AB. So the interval AB, we have a partition. Each of this segment of length delta x. So for example, here we have xk. This point would be xk plus delta x. Which is the length of this segment. Now, one piece would look like this. So here would be one thin strip. Each thin, let's say band, would look like this. And this is the curve. One segment of the curve y equal to f of x. For x between xk to xk plus delta x. So this length is delta x, the width is delta x, xk, and here's xk plus delta x. we will try to compute the surface area of this band. So note that we only compute the area of the band without computing the area of the base. So only the band itself. When delta x is small, the band is a frustum of a cone. So the frustum of a cone is, for example, this is a cone. Then a frustum of a cone is this cone chopped out, this pieces here. So here's one frustum. Here's one frustum. And we will use the formula of the surface area of this frustum to approximate the surface area of this thin band. A frustum. The surface area of the frustum, recall that we don't consider the area of the base. So the two discs here, we don't compute the area. We only compute the area of the surface here. The surface area is, so this circle, the smaller circle, say has radius r1. So the radius of the small circle r1, the radius of the bigger circle r2. And say this length, we call it the slant height. Let's put it s. So the surface area of this frustum is computed as pi r1 plus r2 times s. We can actually prove this formula, the surface area of this frustum, by computing the surface area of this cone minus the surface area of the smaller cone. Then we get the frustum. Okay, now here is the formula of a surface area of one frustum, so one thin band. In our case, what we have is here's one thin band. The surface area of one thin band is pi r1. In our case is the distance from this point to this center. So in our case, because this is a curve y equal to f of x, so this point corresponds to xk, f of xk, xk, f of xk, which is the coordinate of this point. So the radius, the smaller radius r1 here, in our case r1 is f of xk. The other radius is f of xk plus delta x. So this point has a coordinate xk plus delta x, comma f of xk plus delta x. So this length R2 is f of xk plus delta x. So we have R1 and R2. We can replace this formula. The slant height corresponds to the length of this curve for x between xk to xk plus delta x. So here's a curve y equal to f of x, where x between xk to xk plus delta x, the width here is delta x. So we know that this length is delta x, and this length is actually f of xk plus delta x minus f of xk. The reason is that this length is the length here minus this length. This point corresponds to the point xk plus delta x. F of xk plus delta x, which is the coordinate of this point, and the coordinate of this point is xk, f of xk. F of xk. So the length, this length equal to this length, which is f of xk plus delta x minus f of xk. We approximate the length of the curve y equal to f of x by the hypotenuse. Let S be the slant height of this thin band. The length of y equal to f of x, where x between xk and xk plus delta x. The slant height S equal to square root of delta x squared plus f of xk plus delta x minus xk k squared, which is delta y squared. So this is a slant height. So we can do one more step, putting delta x out of the square root. So delta x squared, do the distribution, we have 1 plus f of x k plus delta x minus f of xk squared divided by delta x squared. And we can write this down as square of this quantity, as we have done for the length of the curve. Now can bring this outside of the square root. We have delta x times the square root of 1 plus, so the square root of this quantity. So this is the slant height. Now we have enough information to compute the surface area of one thin band using this formula. So the surface area of one thin band is given as this formula. Surface area of one thin band is pi times R1 plus R2 times S, where S is the slant height. R1 in our case is f of xk. R2 in our case is f of xk plus delta x. So let's put it together. Pi times R1 f of xk, R2 f of xk plus delta x times the slant height. Here is our slant height. So this is the surface area of one thin band. And the surface area of the whole solid is the Riemann sum of the surface area of each thin band when the band is so thin, when delta x tends to 0. So this is the sum when delta x tends to 0 of the sum of surface area of each thin band. So take the sum of all these quantities. So when xk run from A to B, for xk run from A to B. So this one is the limit when delta x tends to 0 of this quantity. Now what we have is the sum of these quantities. So what we have would be the integral of this Riemann sum becomes the integral. X run from A to B, so we have the integral from A to B. Pi is here. F of xk plus delta x. When delta x tends to 0, xk plus delta x tend to xk. F of xk plus f of xk to 2 f of x. So this is 2f of x. This square root, when limits of delta x tend to 0, is the square root of 1 plus, here's by definition, this is f prime of x times, so we have times square root of 1 plus f prime of x square. When delta x tends to 0, we have dx. So here is the formula for the surface area of the solid of revolution.